Hello everyone and welcome. In this video we're going to be talking about some very cool strategies that Mazda is using to not only optimize their exhaust gas flow, but to minimize turbo lag. And so we're going to be talking about the 2.5 liter inline 4-cylinder, which is used in the Mazda CX-9, produces 250 horsepower at 5,000 RPM, 310 pound-feet of torque at 2,000 RPM, so quite a bit of torque early on, and it uses a compression ratio of 10.5 to 1, which is pretty high for a turbocharged engine, so it helps out with efficiency. So we're going to be talking about three of their strategies with the exhaust. The first one, extremely simple. It's short. The shorter your exhaust manifold before you get to your turbocharger, the less energy you're going to lose as that exhaust is traveling through all those pipes and losing heat. So you want to maintain all that heat, maintain all that energy, and have a very short direct path for the exhaust to get to the turbocharger. That's nothing crazy. Lots of manufacturers are doing short routes for their turbocharged engines. But what gets cooler is the exhaust valve which they use, and then the manifold which they use, which you can see goes from 4 down to 3, and then of course down to 1 into the turbocharger. So this valve is pretty neat, kind of like a variable geometry turbo, except it's built within the exhaust manifold. So below 1620 RPM, where you're not going to have a lot of exhaust gases because the engine's just not running that high of a speed, so you don't have that much exhaust flow. You close this valve right here, which is in the exhaust manifold, and so that reroutes everything through a much narrower path. So it's more restrictive, and of course that means it's going to increase the velocity of that airflow. So you're increasing the velocity of the airflow, sacrificing efficiency so that you can spool up this turbo very quickly at those lower RPM. And then once you get into the higher RPM, above 1620, this will open up. Of course, much less restrictive, allows for that higher gas flow where you don't have to worry about spooling up the turbo, and you've got plenty of exhaust coming out. A neat little strategy done within the manifold in order to optimize, how quickly this turbo starts to spool up, and enables you to lower the RPM at which you can start getting some useful boost. So a very cool strategy there. And then finally, we get to the 431 exhaust. And this is really about optimizing scavenging. So a 4-cylinder engine has a firing order, in this case, of 1, 3, 4, 2. So we've got cylinders 1, 2, 3, 4, and then your firing order 1, 3, 4, 2. So I've drawn out each one here. And the reason why they've split the exhaust the way they have is to really optimize scavenging. So you can see when this cylinder 1 fires, if you look at your exhaust pressure, your exhaust energy versus time, when that exhaust valve opens up, you're of course going to have that peak in pressure and energy as that exhaust is coming out. So it's forced out, and then you still have exhaust gas remaining in that cylinder. It's just at a lower pressure, but of course you do have to push out all of that remaining exhaust gas. And so, it starts to kind of drop in pressure as that piston is moving up, and it's forcing out the rest of it. So really, it'd be nice if you could create some sort of suction effect to help pull out that remaining exhaust gas at the end of that stroke. And that's exactly what this strategy is doing. So cylinder 1 has just opened up that exhaust, and so it's hitting that peak pressure that's shooting out, and cylinder 2, so our order is 1, 3, 4, 2. So cylinder 2 was the previous cylinder that fired before 1. So that means it's about to start its intake stroke, and you want to pull the remaining exhaust gases out of that cylinder. So it's low pressure for cylinder 2, very high pressure exhaust gases coming out of cylinder 1. And so when you put these right beside each other, this high pressure pulse that comes out here creates a suction effect. It's called the ejector effect on this port right here. So they're right beside each other, and it creates that suction effect, and it helps pull out the remaining exhaust gases from this cylinder. It's very similar to how a paint gun works, where it sprays air and then it sucks out the paint from below and then sprays that paint onto whatever you're painting. So 1 helps to pull out the remaining exhaust gases from 2. Then cylinder 3 fires. Of course, now cylinder 1 is about to have its intake stroke. So cylinder 3, right beside it, is helping to pull out those gases. Then cylinder 4 fires. That means cylinder 3, our previous cylinder which just fired, is about to have its intake stroke. So they're right beside each other. It's helped pulling those exhaust gases out. And then finally cylinder 2, so your 4th cylinder fires, or your cylinder 2 fires, and then your cylinder 4, you've got that intake stroke about to occur, so you're helping pull out those remaining gases. So as you can see, they're always paired right beside each other using this pairing right here with cylinders 2 and 3. You're always going to have the high pressure and the low pressure right beside each other, so it can help create that suction effect and help scavenge that exhaust, help pull out the remaining exhaust gases. So you've got, that nice fresh air coming in for the intake stroke, and you can optimize power. So very cool strategy all around that they're doing on this 2.5 liter. If you guys have any questions or comments, of course, feel free to leave those below. Thanks for watching.